Tim. Thanks for coming in. And thanks for coming back, everybody. We're almost on time, so we'll see if we can fix that in this session. I am so excited by this session. I've said before that I think fusion energy is the biggest thing to happen to humanity since fire. So I'd like to start by introducing our guests here with a little bit of history. One day, Throg and Oop were shivering in a cold, damp cave. And Throg says, "Remember that forest fire we saw last week? Wouldn't it be great to have a little bit of that in the cave here?" And Oop says, "Sure, but that'll never happen. First of all, how do we convince the gods to start a fire right here in our cave? And did you see the smoke? We'll have to put a hole in the ceiling to let it out. No, it's too complicated. Finish your squirrel and go to bed." Well, Throg kept working the problem, and exactly 25 years later, he figured it out. And he brought fire into the cave. And can there be any argument that the ability to harness fire changed the course of humanity? So now let's jump forward a few years, and a couple of young Canadians are shivering in the middle of a cold prairie winter. They look up at the sun, and one of them says, "Wouldn't it be nice to bring a little bit of that in here?" We met one of those Canadians already. You'll remember Dennis White spoke at our gala a couple of years ago, and he had agreed to be our inaugural speaker at this forum. And a few days ago, his office called to tell us that he contracted COVID, and he wasn't going to be able to join us. And they said, "So you wanted a world-renowned physicist from the Canadian prairies who's leading the development in the technology of fusion?" We said, "Well, yes." He said, "Well, we have another one."
All right.
So that's the good news. So we were introduced to Professor Marmar, and who knew, from Winnipeg, and he did his undergrad and physics degree at the University of Manitoba, where some professor clearly saw his potential and advised him to apply to Caltech or to Princeton for grad school. And he went to Princeton, and during his grad work there, it happened to be the oil crisis in 1973 or thereabouts, and he got interested in alternative energy sources. And he did experimental work at Princeton's plasma physics lab, and he's worked in that field ever since. Since joining MIT, he's been a research scientist, principal research scientist, senior research scientist, and head of the Alcator project at the MIT Plasma Science and Fusion Center. He's now the head of Magnetic Fusion Experiments Division and Associate Director for Government Relations for the MIT Plasma Science and Fusion Center. His list of publications in the area is extensive. It's safe to say he will not perish. He has been a member of the Fusion Energy Sciences Advisory Committee and chair of the U.S. Fusion Facilities Coordinating Committee. And he's an expert member of the ITER Science and Technology Advisory Committee, a member of D3D Executive Committee and member, and D3D Program Advisory Committee. ITER is an international nuclear fusion research and engineering megaproject in France, so probably the biggest one in the world, and I think the one you're working on here is the smallest one in the world, if I'm not mistaken. And D3D is a tokamak that's been operated since the 80s in San Diego. So a great resource in this field, and I'm looking forward to hearing about how quickly I can bring a little bit of the sun into my living room. Our session with Professor Marmar will be as a fireside chat with another amazing and accomplished Canadian from another small town. Catherine Lefebvre was born and grew up in Saint-Romain, Quebec, a village of just 600 inhabitants. She claims there were more sugar shacks than houses, and only one other kid on her road to play with. Her parents were both family doctors in the village, and she was always fascinated by science, thanks to her parents, and particularly her father, who's not only a doctor, but also an electrical engineer. I knew I liked you more than I should. Today, Dr. Catherine Lefebvre is Vice President of Strategic Business Development in North America at Pascal, a full-stack quantum computing company. Quantum computing is weird stuff.
We can't get it in the cave.
Yeah, powered by a fusion reactor, which it probably will take, right? Prior to joining Pascal, Catherine worked at the quantum ecosystem as an in the quantum ecosystem, as an innovation ambassador in US and Canada at M Squared Lasers. She's also a scientific advisor in quantum technology for the Quebec government and a scientific liaison officer in artificial intelligence for the National Bank of Canada and then for Element AI. She holds a PhD in molecular physics and theoretical quantum chemistry from Université Paris-Sud and Université Laval, and she was a postdoc fellow and research associate for almost a decade at the Université de Sherbrooke and the Canadian Space Agency. I'm sorry I'm mangling the French. I used to I used to work in French and it's left me. So, and she also has training in science diplomacy and is currently serves as an expert for the Geneva Science Diplomacy Anticipator, which is a neat sounding thing. I want to hear more about that, for their initiative on quantum computing for humanity. She's based in Boston and is a fine example of the great Canadians that make up the scene. So here we have two highly intelligent, highly educated, highly accomplished physicists having a conversation. What could go wrong? Catherine has assured me that she'll keep the conversation to a 6th grade level.
Yes.
So, Roger, you and
I'm
I
okay.
should be able to fit most of it. Catherine, take it away.
Thanks very much.
Thank you, Scott. I don't know if this is working. I've always been told I have a soft voice, so I'm taking the mic in case it's
Not
working.
on.
It's not working.
It's
You
not.
can hear me? Okay. Then
You're on mute.
I'm on. How do you like my background?
Yeah. I'll play with it
So
later.
then we'll start with equations and.
I hope not.
No. Well, thank you very much for coming here. It's an honor to sit with you today.
Well, it's my pleasure to be here.
And 50 years in fusion, that is something,
Almost.
right?
Not-
49?
Yeah, maybe. Graduate school, yeah.
Right? Yeah.
I don't like to dwell on that. But I think, yeah, that's true. And for a long time, we thought fusion was still quite a distance away as a realized commercial energy source. But there's been some technology breakthrough that we think will actually change that timeline. And we're looking at more like 10 to 15 years from now to probably of order 10 years to have fusion energy on the grid. That's the plan, our current plan. And I can tell you more about
Yeah, we look
that as we go.
We actually look forward to hearing more about this. But first of all, we're here because we're Canadian. And Scott gave us an introduction, but I would love to hear a bit more of your background, what brought you into science and
Sure.
specifically into fusion.
So I grew up in Winnipeg, and we didn't know better, but it was a great place to grow up, actually. It was a wonderful, warm environment, not literally, but figuratively. And, well, we used to have an old song we sang there, well, it's 40 below in the winter, and it's 20 below in the fall, and it rises to 0 in the springtime, and we ain't got no summer at all, which is actually false. It's actually very hot in Winnipeg in the summer, as you may know, if you can avoid the mosquitoes. Anyway, I got through college and was very interested in physics in college. I was interested in math even earlier, probably high school. Physics wasn't really taught much in high school in those days. It's a little better now, but we got to physics in the first year of college at university and at the University of Manitoba. And once I saw a little bit of calculus, I thought this is pretty interesting stuff. And then you can kind of start to understand how the universe works a little bit, at least a piece. And as Scott said, I went to Princeton after I finished my bachelor's degree and got interested in plasma physics and fusion as an energy source. So that's what I've worked on ever since, and we've made tremendous progress over the last decades. And now we're at a point where we can really get to the finish line. So I'm really excited about that.
So let's take a step back and let's set the stage. What is fusion? And then we
Great.
hear, like, we're physicists and we get all those questions, right? Oh, you're
Yeah.
a physicist, you can explain me everything, right? And then
Yeah.
a lot
Well,
of confusion between fusion and fission.
Sure. So what is fusion? It's the joining of two very light nuclei. In this case, we use hydrogen, actually heavy forms of hydrogen. Hydrogen is the simplest atom. It consists of one proton and one electron. That's a hydrogen atom. And the nucleus is the proton, which has a single positive charge. The electron is negatively charged. The atom is neutral. But there's a form of hydrogen called deuterium, which chemically is essentially identical to hydrogen, but it has, in addition to the proton in the nucleus, it has a neutron, which is a neutral elementary particle. And the neutron and the proton join together through the nuclear force, but it really doesn't change the atom significantly. Unfortunately for us, about 1 out of every 6,000 hydrogen atoms on Earth is actually a deuterium atom. Now 1 in 6,000, maybe that doesn't sound like much, but there's a lot of hydrogen on Earth. Like all the water, each water molecule has 2 hydrogen atoms. So there's enough deuterium fuel through fusion to power our current energy needs for of order 500 million to 1 billion years. So that's probably a good goal to actually harness that. That's the plan. How does it work? Well, if you take 2 of these nuclei and you get them to get close enough together, they will actually stick together and make a helium nucleus. And in that process, you release some energy because the mass of the helium nucleus is slightly less than the combined mass of the 2 particles, the 2 deuterons in this case, that you join together. And that slight difference in mass gets multiplied by the square of the speed of light to turn into energy. And one fusion reaction gives you about 20 million times as much energy as you get from burning 1 molecule of methane, 1 molecule of natural gas. So you need about, for an equivalent amount of power, 20 million times less fuel. So for a fusion reactor, working for about a year, all of the fuel that you would need can be put on a small truck. And so that's really great. Another important aspect of fusion is that the product, the helium nucleus, the helium atom in the end, is completely benign. So it's first of all, you don't make much of it, but it doesn't matter. You don't have to worry about disposal or safety for the helium. Now it turns out in the reaction, it's a little more complicated than what I said. You also produce a free neutron with a lot of the energy. The neutron then leaves the reaction and has to be captured and warm something up, a bath of material. We call it a blanket. You heat that up to maybe 800 degrees C. You then run that through a steam cycle, and you can run a generator with that, make electricity. But
back to water.
Back to water,
right?
Yeah, that's right.
Yeah.
But the neutron, in the process of going through the materials that you built your reactor out of, can also produce some other nuclear reactions which can make some additional radioactive isotopes. Not very much, but enough that you have to think about it. So it's not completely free of radioactive products. Now fission is the opposite of fusion. Fission is taking a heavy nucleus like uranium or plutonium or thorium and allowing it to split into 2 smaller subelements. And that turns out to also produce a lot of energy, actually even more than you get from one fusion reaction. Fission has the advantage that it happens spontaneously. You don't have to bring the particles together to make it happen. But it has the disadvantage that the products that you get are inherently hard to deal with. You end up inevitably with long-lived radioactive material that you have to somehow corral, store, and when I say long-lived, we're talking about millions of years. So it's kind of, that goes way beyond our society, any time scale that we're used to dealing with. So that's one of the sociological challenges. It may or may not be a technical challenge with fission, but it's definitely a we don't want this stuff anywhere near us challenge, and we've seen that play out politically, certainly in the US. There are working fission reactors, although it turns out now there are fewer all the time. They're being shut down faster than they're being built. And that is not really a reflection of the technology, it's a reflection of some of these sociological issues and a few very high-profile accidents, which probably could have been prevented, but they weren't. I mean, you're familiar with 3 Mile Island, with Fukushima, with Chernobyl. These were very bad events, particularly Chernobyl and Fukushima. So fusion doesn't have that problem.
And it's easier to deal with helium, and we can
So
blow
the
balloons.
helium is not a problem. It turns out you won't make enough helium to blow up your balloons, but anyway, so it goes. It would be nice if you did, because helium also is in short supply. Anyway,
Indeed,
there are a few critical things about fusion I didn't tell you. It turns out it's very hard to get these two hydrogen nuclei to get close enough together to actually stick together. You have to get them so close that the nuclear force comes into play. How close do you have to get them? Well, I don't know how to explain this exactly. It's 10 to the minus 15 meters is the distance that you have to get them near each other. And unfortunately, these particles are both positively charged. I don't know if you ever learned in high school science or chemistry, positively charged particles repel each other. They don't like to get close together. They feel an electric repulsion. So you have to overcome that force to get these two particles to stick together. And the only way to do that is to get them up to very high energy. About 100,000 electron volts is the unit that we measure the energy in. Electron volt is the energy that a singly charged particle gets if you accelerate it through a 1 volt potential. So if you take two copper plates and you attach a battery to them, which is say 1.5 volts, and you get an electron to leave one plate and go to the other one, it'll have 1.5 electron volts when it hits the other side. So we need to get these particles up to 100,000 electron volts. You could, in principle, get fusion to work by simply accelerating your deuterons and slamming them into a target. And you will actually make fusion reactions that way, but you'll never make net energy because the electric forces are too big and the particles mostly just slow down without ever fusing. So the way you can get energy from fusion is you actually have to create a charged gas that we call plasma at very high temperature so that the particles can keep colliding without losing energy over and over again until once in a while they actually will fuse. Now, what temperature do you need for that to happen? Turns out you need about 200 million degrees centigrade. Kelvin, choose your units, it's the same number.
It doesn't matter anymore.
Yeah, that's correct. So 200 million degrees. So this, by the way, is the way the sun makes its energy, although the sun does it with ordinary hydrogen, not with heavy hydrogen. And the sun can only get away with doing it with ordinary hydrogen because it takes, on average, 1 billion years for the protons to collide and stick together in the sun. We can't wait that long. So we need to do it with deuterium, and it turns out there's another form of hydrogen called tritium, which has yet another neutron, so it weighs 3 times as much as ordinary hydrogen. Again, chemically, just like regular hydrogen. And when you take 1 deuteron, 1 triton, that's when you get this 20 million times the energy. If you can get the medium, the plasma, up to 200 million degrees and hold on to it for a few seconds with enough particle density, and it's not very much density, it's about 1/200 millionth of the, well, not 1/200, about 1/5 millionth of the density of the air in this room. So it's very, very low density stuff, but because it's so hot, it actually has pressure that's above atmospheric pressure, about 10 atmospheres actually, is what you need. And you need to hold on to it for a few seconds before it loses its energy, its temperature, before it cools off. And when you can do that, if you can then also hang on to the helium ions that are produced, you can heat more cold fuel, and that becomes a self-sustaining reaction. Now you might ask, how can we possibly hold on to something at 200 million degrees? How can we even get it to that temperature? Well, you have to do both. You have to hold on to it and heat it, and it bootstraps its way up, and we do it with magnetic fields.
So let's get closer to here in Boston at
Sure.
MIT and exactly like what is the way that MIT has been, the approach that you're taking, and what is so unique?
Yeah. So we've known for a long time that the best way to hold on to this plasma is to use a strong magnetic field. Why does that work? It's because charged particles, turns out, can't easily move across a magnetic field. So if you have a magnetic field in this direction and a charged particle trying to go this way, it just goes in a little circle and it stays kind of where it is. Now it turns out there's no force on the charged particle if it moves parallel to the magnetic field. So if you set up a long, straight magnetic field, which you can do with electromagnets, a bunch of electromagnets called solenoids, you will hold on to this plasma in 2 dimensions, but not the 3rd dimension. And you could build a fusion reactor that would actually make net energy if you made it long enough. It turns out the particles are moving so fast at 200 million degrees that the length of that device would have to be about 50,000 kilometers. So that's probably not practical. The sun, by the way, does it using gravity. That's how the sun holds on to its plasma, which works great if you can be the size of the sun. We can't do that on Earth. It's not possible. That's the way all the stars make their energy, of course. It's the same process. Okay, so now you have this long, straight magnetic field which doesn't work because all the power ends up at the ends. It just leaks out the ends. Well, there's a topology called the torus, the donut, if you like, which if you take the magnetic field and bend it into a circle, now suddenly the particles which are spiraling around the field, they go around and around, and they stay inside that donut. It turns out it's not quite that simple. Nothing's ever quite that simple in our field. If you have just a simple toroidal magnetic field, the particles themselves are a little devious, and the electrons and the deuterons tend to drift apart from each other if you have just a toroidal field. And when they do that, they make a big electric field in the vertical direction, and that electric field interacts with the plasma and makes it expand in radius, and it hits the walls in about a microsecond. So that didn't work either. So in about 1950, a guy by the name of Lyman Spitzer, who was at Princeton actually, figured out that you could make a twisted magnetic field. And if you made the magnetic field helical, then these drifts cancel out and the whole thing works. And around the same time in the 50s, a couple of guys in the Soviet Union were working on the same problem, and they figured out, and the way Spitzer did it was with very complicated twisted magnetic field coils. which turns out didn't quite work very well in the 50s because we didn't know enough back then, or they didn't know. I didn't know anything back then. But they didn't quite get it right, and it didn't work. But the guys in the Soviet Union figured out that if you ran a current through the plasma, it turns out plasma is a really good electrical conductor, about the same as solid copper actually at room temperature. If you run a big enough current through the plasma itself, that produces another magnetic field in addition to the toroidal one, and you get a helical field, and that solves the problem, and that's called the tokamak. And that was first demonstrated in the late 50s, and there's a whole history behind that. But anyway, and we've been working on that ever since. Now, what did we do at MIT? We took that idea and we said, let's make the magnetic field as strong as we possibly can. Because we know if we do that, the size of the device that we need to hold on to this hot plasma can be made smaller. And it turns out that the size that you make it is inversely proportional to the field. So if you double the magnetic field, you can make your fusion reactor half the size. That turns out to be a big deal because that's about a factor of 10 in volume and about a factor of 10 in cost for the actual device. So that brings us to the 1970s, 1980s, 1990s. At MIT, we were pushing this very high magnetic field approach, and we did it using copper conductors for the magnets. But we knew that copper was never going to work in a reactor that made electricity because you need too much power to run the magnets. So we looked at this and we could calculate very easily that to make a reactor of the size we needed at the magnetic fields we could get with copper coils, you would need about 1,000 megawatts of electric power to run the magnet. Unfortunately, that's all the power you were going to get out of your fusion reactor. So what you were going to do is basically make this thing that just heated up and never made any electricity. So that was not going to work. You needed a fission reactor to run your fusion reactor magnet. So that was a non-starter. But it turns out there's something called superconductivity, which you may have heard of. There are materials, usually things that have to be made very cold, like liquid helium temperature, which is 4 degrees absolute, almost absolute zero. And they have this almost magical property that their electrical resistivity goes to 0. It doesn't just get small, it actually goes to 0. This is a quantum mechanical effect. You might be interested in that, in your field. But as a result, if you can make your magnet out of superconductor, now you're in business. But the best superconductors that anybody came up with until about 10 or 15 years ago had a limit on how strong the magnetic field they could make would be. It's just related to the physics of how the superconductivity happens. If you put a strong magnetic field on a superconductor, it suddenly makes a transition to a normal conductor or even an insulator and no longer will carry the current. About 30 years ago, some people in Switzerland discovered a new material called high temperature superconductors, which was kind of a lab curiosity for a long time. They actually won a Nobel Prize for this shortly after they discovered it because it was so interesting in terms of the physics. But people didn't know how to make it into magnets. Now I say high temperature superconductor. These materials can be superconducting at even liquid nitrogen temperature, which is around 77 degrees Kelvin. That turns out to be a big advantage technically, but it's not the main reason we're interested in them. It turns out the high temperature superconductors work at much higher magnetic fields. So now suddenly we have the possibility of marrying two ideas: the very high field magnetic bottle, the tokamak, and the very high field superconductors. And people have figured out in the ensuing decades how to make these superconductors into very thin films that can be deposited on a stainless steel substrate and then turned into a ribbon, which can then be wound into a magnetic field coil. People have made small coils at very high magnetic field out of these. We need coils that are kind of a meter across for our device. So just as a show and tell, this is a copper cable, which will carry about 1,000 amperes. And this is high temperature superconductor ribbon, which will carry the same amount of current as this cable. And it will do it without any, once the current is flowing, you don't need any power to maintain the current. And in fact, if you took this little ribbon and cooled it in a bath of liquid nitrogen, it would become superconducting. So we're going to run our device a little colder because you get a higher field when you do that. But anyway, so that technology needed to be demonstrated. Some of our graduate students who finished around 2015, 2016, 4 of them actually, who worked in my group at MIT on the tokamak that we were operating there, plus some of the more senior people at MIT came together and said, how do we leverage this technology and make it happen?
So the technology is moving out of the lab,
It's
out of
moving
MIT
out
lab.
of MIT. So these 4 graduate students founded Commonwealth Fusion Systems, and their goal is to commercialize fusion. So they had a few, first of all, they raised quite a bit of money in their first round. They raised about $200 million in 2018. Which was a lot for a first round
That's a lot.
for 4, left behind the year's graduate students. That's how I saw them at the time. That was great. And what were their milestones? Well, one was to demonstrate a full-scale magnet made out of this material, which had never been done. And the only way to do that quickly that they could see and we could see was to actually join forces and do it at MIT. So they took their $200 million, they spent some of it on other things, but they spent some of it on our group to actually help them build up, based on the fact that we've been doing this research and we had the technologies that were needed to actually do this demonstration. And in under 3 years, we demonstrated a magnet at the magnetic field that's needed for the next step and at the right scale, the meter scale. And that successful demonstration was done in September of 2021. And most of that work was done through the height of the pandemic, actually. And it turns out you can't wind magnets on Zoom. You actually have to go into the lab. So there were a lot of challenges.
And then this May, last month, you extended a partnership
So we
with
did. So then,
CFS.
but perhaps more pertinent, we'll get to
Yes.
that. The result of having that successful demonstration was Commonwealth Fusion was able to do a second round of fundraising, and they raised $1.8 billion in that second round. And that's enough to build a demonstration tokamak that will make net energy. So that's the plan, and that's
So net energy